everyone, let's talk about problem 2, which says an inlet pipe can fill a pool in 4 hours and a drain can empty the pool in 6 hours. How long will it take the pipe to fill the pool if the drain is left open? So the pipe can fill the pool in 4 hours, so its rate for filling the pool is 1/4 pool per hour. The way I got that was it can fill one pool in 4 hours. So we would have 1/4 of a pool per hour. Okay? And the drain is emptying the pool in 6 hours. That should be so. So the rate it is emptying the pool is 1/6 pool per hour. So one pool in 6 hours. So it can drain the pool 1/6 of a pool per hour. Okay, so we're going to let T be the time that's worked. And since the pipe is filling the pool and the drain is emptying it, they're fighting against each other, so we're going to have to subtract. In other words, we're going to fill the pool, that's going to be positive, and then we have to subtract or take away the water that the drain is emptying. So our work done will be the work that the inlet pipe has done minus what the drain has taken away. So work is one pool. This would be the inlet pipe. So the rate that the inlet pipe was working was 1/4 of a pool per hour. And the time is what we're trying to find. So we're just going to let T be time. Okay, and then subtract the work that the drain pipe is doing. So 1/6 of a pool per hour times our time. And so 1/4 T minus 1/6 T would be 1/12 T. If you don't like fractions, you can use a decimal here if you want. And then to find T, divide both sides by 1/12. In other words, multiply both sides by 12. And you get your time is equal to 12 hours. So it would take 12 hours to fill the pool. Okay, number 3 says 2 generators are able to produce 10.75 watts of energy in 2 minutes. If one of the generators can produce 10.75 watts on its own in 18 minutes, how long does it take the other generator to produce the same amount? So what we have here is one of the generators can produce 10.75 watts on its own in 18 minutes. So its rate would be 10.75 watts in 18 minutes. So it would be 10 divided by 18 watts per minute would be its rate. And that's what I figured out right here. So it also asks us how long does it take. So we want to know something about time. So let's let T be the length of time it takes generator B to produce the same amount of energy, because that's what the question's asking. So we don't know what the other generator's rate is, so we're just going to let R be generator B's rate that it's working. Okay, so when the generators are working together, 10.75 watts of energy is produced in 2 minutes. So let's think about running the generators for 2 minutes. So for 2 minutes, they're going to produce 10.75 watts. And we're going to have the rate that the first generator is working at plus the rate that the second generator is working at times the times. So this will be the work produced by the first generator and the work produced by the second generator. Okay, so the first generator we said was 10.75 over 18 watts per minute. And then times 2 minutes, because that's what we're saying. We're going to assume that it runs for 2 minutes. And then for the second generator, it's working at R watts per minute, and it's working for 2 minutes. Okay, so we want to solve for R. So subtract the 10.75 divided by 18 times 2 from both sides. Divide both sides by 2. I type that in my calculator and I get 4.7777 so on watts per minute. But the question is asking for time, not the second generator's rate. So we need to come up with another equation, and let's just use the second generator. Okay, so it wants to know how long it will take to produce the same amount. So the same amount is at 10.75 watts. So plug in the 10.75, the rate that generator B is working at is 4.7777 watts per minute times time. So divide both sides by 4.77, and this would be 2.25 minutes. Let's talk about problem 4. A certain coal plant consumes 1,604 tons of coal in 5 weeks. There is a stockpile of 10,505 tons of coal available when the plant starts operating. After 4 weeks in operation, an additional boiler capable of using 2,300 tons in 4 weeks is put online with the first boiler. In how many more weeks will the stockpile of coal be consumed? Well, it's asking us how many more weeks, so let's let W be how many more weeks it'll take for the stockpile to be consumed. So that will be our answer. Okay. The first plant consumes 1,400 tons of coal in 5 weeks, so its rate will be 1,604 divided by 5 tons of coal per week. And so that's what I have here. Then the second boiler is capable of using 2,300 tons of coal in 4 weeks. So its rate will be 2,300 divided by 4 tons per week. And that's what I have here. Okay, so let's look at the equation. So work is equal to rate times time for the first boiler, and then they're working together, so this will be plus rate times time of the second boiler. So the total work that they're going to do is like consume this entire pile of coal. So the work will be 10,505 tons of coal. So for the first boiler, we said the rate was 1,604 divided by 5. And then the time. Well, W was how many additional weeks or how many more weeks? Well, this first boiler was working by itself for 4 weeks, because it says after 4 weeks, the other one is put online. And so it works for 4 weeks, and then it also works for the W additional weeks. Okay, so that would be the time, W plus 4. Plus the second boiler's information. So the rate of the second boiler is 2,300 divided by 4 tons of coal per week. And the second boiler only worked for the W additional weeks. So we have this equation. We distribute and combine like terms and divide, and we get W is equal to 10.29448 additional weeks. Okay, please take a look at the next video when you're ready.